Alright, silly people, here's the situation. We're going to be calculating the efficiency of a light bulb as a function of its temperature. Um, and so we've got this equation, which is the intensity of the light bulb. The efficiency is given by these guys, and it boils down to doing one little integral between lambda 1 and lambda 2, which represents the limits of the visible light spectrum. This integral that you can't really do analytically. Right. Um, and so, yeah, the first part of the problem is to just plot this integral as a function of t between 300 to 10,000 Kelvin and see if we can see a maximum for the efficiency, right? Um, and so I am just going to use our old friend Gaussian quadrature to do the integral. So I had to copy this code cell down from the last chapter's notebook so that we can do Gaussian quadrature. Again, this is on the online resources for the book, so just go grab that. We can get into the code. I'm gonna import numpy as np and also matplotlib.py plot as plt. For the physical constants in this problem, you actually want to use quite a few significant figures on those to get an accuracy down to 1 Kelvin for the maximum. So I'm just going to read off all the significant figures that are on the Wikipedia pages for each of these constants. So for H, it's 6.626, 07, 015, E minus 34, and then C, the speed of light, is 2.99792 E8, and then KB, Boltzmann's constant, was 1.380649 E minus 23. Okay. We also need the lambda 1 and lambda 2, which again, those are the limits of the visible light spectrum. So it goes from 390 nanometers to 750 nanometers. Right? Yeah, there they are up there. Okay. We can define the integrand f of x as usual, just by doing the numpy exp of x divided by, well, no, that's not even that. It's x cubed divided by numpy exp of x minus 1, right? Yeah, that's the integrand. Okay, and then we can do a function called eta, which is going to calculate the integral as a function of t. The upper bound and lower bound are both determined by the physical constants. The lower bound is going to be h times c divided by kb times t times lambda 1, or no, this is lambda 2 down here. And then b was the upper bound, so h times c divided by kb t lambda 1. Alright? Right? Let me check the... Yes, lambda 1 up top and lambda 2 on bottom. Okay. Then you do your Gaussian quadrature bit. You define how many sample points you want to do. Newman recommends 100. We create an x and a w variable equal to Gauss xw of n, and then we create an xp list, which is 0.5 times b minus a times x plus 0.5 times b plus a. And then you create a WP list, which is just 0.5 times B minus A times W. And then you create a sum that you're going to add on to, and you go 4K in range. And add onto that sum WP indexed k times the integrand, call it XP indexed k. Right. Afterwards, you can return the value of the integral, but it's also multiplied by 15 and divided by pi to the fourth. So we're going to say s times 15 divided by p dot pi to the fourth. Right. So we are just plotting it, so let's create an input list for it to run through in space from 300 Kelvin to 10,000 Kelvin. It doesn't really matter to get high fidelity for the plot for us to see where the maximum is, so I'm just going to do 1,000 points for this. Otherwise, it will take forever. Create an output list called eta ls. Just do 4t in TLS. Eta ls dot append eta of t. Yeah, so then you do plt dot plot TLS versus eta ls, and after this gets done running, we can see if we find any maximums. Oh, there it is. So yeah, there is a non-zero maximum for the efficiency, somewhere in between 6,000 and 8,000 Kelvin. The next part of the problem is to find that maximum using the golden ratio search method. So what I'm going to do is I'm going to take all of this stuff that we've done so far, pretty much, copy it down to the next cell, and yeah, figure out where the maximum efficiency is. So the idea with the golden search method, which I'm going to do in a function that I'm going to call gsearch, is you start with a value of x4 and x1, x1 being a point before where I think the maximum is, so somewhere like 6,000, and then x4 being somewhere above the maximum, so somewhere like 8,000. So x1, x4. You create a target accuracy. We want our accuracy to be 1 Kelvin for this. So accuracy is actually going to be 1. And also arbitrarily large value for the initial error, 6.02 E23. Basically, the first thing that you want to do is you want to define what the golden ratio is, and that is actually just a fixed number, 1.618 for that. Create a error loop while the error is greater than the accuracy. You can, in here, calculate what x3 and x2 are using the golden ratio, and your guesses for x4 and x1. So x3, you have that be equal to x4 minus x1 divided by z plus x1. Similarly, you'll take that value for x3 and use it to calculate x2. So that's going to be x3 minus x1 over z plus x1. Right? So that's pretty cool. Now you can check if, and I should probably put these back tab level. You check if the function that you're doing has minimums at x3 or x2. And since we're actually doing maximums rather than minimums, all of the function calls that we're going to do are going to have a minus sign up front. So if, and I'm doing in parentheses because this is going to be a big Boolean statement, but it's going to be minus eta of x3 if that is less than minus eta of x1, and it's also less than minus eta of x4, then you will be able to proceed. But otherwise, you might also check if eta of x2 is less than eta or minus eta of x1, and minus eta of x2 is less than minus eta of x4. If either of those happen to be true, then you can proceed with the code. Otherwise, you can have it break the loop because there's no point in continuing at that point. You just made a bad guess. Right. So in here, you're going to create another if statement. So if, at this point you want to check if eta of x2 is less than eta of x3, right? So if minus eta of x2 is less than minus eta of x3, in this case you will make x4 equal to x3, replacing the values, so honing in on the where the maximum actually is. Otherwise, you make x1 equal to x2, right? And at this point, you can calculate the error. Just going to make it the absolute value of x4 minus x1. And if it gets all the way to the end of that loop and gets an accuracy that's less than 1, or an error that's less than 1, then you can have it return x3 plus x2 over 2. So the midpoint between x2 and x3 at that point will represent where the minimum actually is. So yeah, we already said that we think that the maximum is going to happen between 6,000 Kelvin and 8,000 Kelvin. So we can print G search, calling those values, and we'll see if it finds where the maximum is. Gauss XW is not defined. Oh, my runtime disconnected. Run this cell again. This should work now. So that was pretty quick. It found a maximum at 6,928 Kelvin. That's where the maximum efficiency of the light bulb is, and that seems like a value that is believable. Is it practical to run a tungsten filament light bulb at this temperature? No, it is actually, that's hotter than the surface of the sun. I wouldn't call it practical or even like a reasonable thing that you can even do. So no, but that's where the peak efficiency is, so maybe one day. All right.